I did some more sets. I did some work. Weird, like Chronic side, like she would make Chronic explain all of our things because like she like didn't understand them, I guess. I don't even understand what it means. Like literally had to go because I left him. He didn't go to class yesterday. But he went after the class ended and like talked to her and she literally explained every single period and she like gave us the cruise was like they were like one of them was not all good. I completely misunderstood. But I have two problems this week.
It went pretty well, yeah. You could like work together.
7 but 8 Okay, it's not an issue. But I have like analysis material there. That's gonna be fun.
Yeah.
There's a third piece set, but he's not reading it. Can't everything else just go on hold? What's your to do? Did you give me one? Dude, you are so nice. Except for I already have this. I can like go upstairs one more. It's actually faster. Random variable. It's random variable. Bernoulli trial. You like writing up pencil? Imagine making mistakes. It's the last one said. There's only 7 less than her. Because she was like, yeah, no, our term like but it wasn't just us, it was like everybody.
Yeah, those were all.
I understood like it was none of your peers, like the whole class, especially here. Like on my office hour at some point,
Like the it's
he just went. I didn't think he would go because he didn't go to class. Like the class would never have it. The class would go. Really, he said that I don't. You know, teams hour. Yeah, she doesn't care. She's like, you know, it's just.
No, it's like
Cost $350. Stack exchange. There you go. We don't have those for our class. She's like taking like this.
Good morning.
She's not teaching out of a book. She's like just teaching like the notation you use. She uses on the same notation. It's just like then like she was drawing stuff from the comments and I was like, oh, it's not prepared for the chords. And she was like, obviously you guys have seen this before. But that seems wrong.
All right. Ooh, thud. Good morning, everyone. People are so rude. Put your trash away. All right. Should we do some set theory today? It's M&M's later. Woo! Yeah. Okay, so where are we? We have a pairing convention. When we talk about ordered pairs, a relation is a set of ordered pairs, and a function is a relation so that there's only one output for a given input. This is another way of saying it's function-like, right? So if x is related to y1 and to y2, then those y's were actually the same. There's only one. Okay, so last time I managed to get jumbled up in my notes and skip a few things and then misstate something. So I apologize for that, and I'll try and clarify now. Firstly, what are we exploring? We're exploring when is f inverse the reverse relation for f a function. Right, that's what we're interested in so far. And I missed a theorem at the bottom of page 2 if you're following along in the notes. Okay, so the theorem says if we have two functions and I want to compose them, then I'll tell you what the domain of that composition is. Right, that's how we're going to understand this theorem. Okay, so theorem. Okay, good, everybody can see. There. Oh no, get out of there. So if f and g are functions, did I write this the right way around? It would be helpful if I did. Oh, I didn't. No, I did. I'm so smart. Hooray. Okay, so if f and g are functions, then f composed g is a function with domain. Okay, so it's the collection of things that you can plug into G, right? So things in the domain of G whose output you can plug into F, right? Okay, so if you're thinking in terms of other math classes, you might think of this as the definition of the composition function, right? You define composition by saying I plug one into the other, and the domain is whenever I can do that, okay? But we have defined composition as an operation on relations, right? So we can combine any two relations. In fact, we've actually defined how to compose arbitrary sets. They don't even have to be relations. Okay, so for us, this is actually a theorem. It's a result that comes from our definition of composition, which is much more broad than in like analysis or algebra. Okay, but it does, what the theorem says is our definition of composition did what we wanted it to do. So whenever you are in math and you try and generalize a definition you already have, so make it work in new contexts, you need to make sure it still does what you meant it to do in the context you understand. Okay, so this here, it tells us that our composition, like, it does what we expect it to do. Okay, I don't want to prove this. I just wanted to state it. If you're interested, you can prove it yourself. So you actually have to prove that the composition is a function. So you have to prove that if f composed G sends x to y1 and to y2, then those y1s and y2s were the same. Okay, because that would prove it's a function. And then you'd have to compute its domain. So, in fact, actually, this might just be literally this is the definition, but if you just compute the definition of the domain of the composition from the definition of the composition, it just equals that immediately. The idea, though, is if we have these bubbles, where's my colored chalk on? Hooray. All right, so here we have the domain. What am I doing first? G. This is the domain of G. here is the range or codomain. Let me put codomain. No, let's not put codomain because I haven't defined that for you. This is the range of G. And then in red, we have the domain of F. And then we have over here the range of F. So if the idea is, right, like we have an input to G, and it might go over into the red thing. And if it goes over into the red thing, then I can plug it into F, right? So this here would be a valid input for the composition, whereas this thing isn't, right? It stops. So this is just not in the domain of the composition, that's all. I'm overusing arrows now. Let me make it squiggly so you know it's not the same. Not in the domain of F compose G. Does that make sense? Okay, so you just pick, you try and string together the arrows, and we only take the arrows that you can go all the way from the beginning to the end. All right. Okay, so is this how I want to state this? Oh, it's an example, not a theorem. Okay, I was like, that looks bad. I'm getting confused by my own handout. All right, so let's do an example. Okay, so let's suppose we have some function, that's not how we write those, f that goes from A to B is injective. Do you want me to think of a particular example? Let's do that. It helps. X cubed. And then A equals B is the reals. Okay, so if we're injective, we know we have an inverse function. Right, we always have an inverse relation. I can just turn the relation around. But kind of step one answer to this question is f inverse is a function when f is injective. Okay, so hence f inverse from B to A is a function. What's the function in the example? I know this is silly, but let's. What's the inverse function to the cube? The cube root, right? I'll write it both ways. Okay, so the question is, f inverse compose f. What is this thing? That is the question. What is this? Okay, so we have a function f, we've got a function f inverse, and I've composed them. So what kind of object do I get out? A function, right? It's a function. It's not just a relation, it's better than that. So f inverse composed f is a function. And what's its domain? So we have to ask ourselves, which things in the domain of f, land in the domain of f inverse? Right, because those things will be in our domain of our composition. So if I plug something into f, it gives me y. Under what conditions is that y in the domain of the inverse? That's the question. So let's have a look in our example. Right, I plug in an x to f, I get x cubed. Under what conditions can I take the cube root of that? Tell me. I can always do it, right? I can take the cube root of any real. Was that an accident? No, it wasn't an accident, right? Because f inverse is defined to be take f and turn it around, right? So it accepts all of the y's. So it's a function whose domain equals the domain of f. So saying which y's are in the domain of f inverse is just all of the y's, right? Because f inverse, turn them all around. Sorry, is it my beard or what's scratching? Okay. Oh, Lord. Am I going to have to be really preppy for the class today? Okay. If I pass out, this is for you. All right, so here's the okay. So there's its domain is f. Of course, and then other question, what's its formula? So what is f inverse of f of x? So we can look in our example. If I cube something and then cube root it, what have I done? Net. Tell me. Done nothing, right? I've done nothing. So I got back where I started. Okay, so this is x, right? Okay, so we've got a function whose domain is the domain of f and always spits out whatever you put in. All right, that function has a name. It's called the identity. Right, so this is equal to the identity on A. Okay, so we often denote this way. So ID is for identity. The subscript A tells you what my domain is and my range, I guess. Okay. So like this, I don't think this is a surprise to anyone who has taken went through high school. But like the inverse function, like what it does is it undoes the action of f, right? Like with respect to composition. But okay, and many texts like define the inverse that way, right? It's the function that undoes f. Like if you look in a bunch of textbooks. But again, we have a more general definition of inverse, right? Because our inverse works on relations, and in fact, all sets. So like this is a theorem for us, right? The inverse does what we want it to do. Okay, scroll down. All right, and then I got to this theorem. All right, as you can see here, this theorem as written is ungrammatical. And I thought that meant that I'd made a typo. But what it actually meant was I needed to look in my notes where I fill in the blanks, and I needed to fill in the blank. And I forgot how I teach my own class, which is a little bit embarrassing. Okay, so the way you complete this is not like how I said last time, because then it doesn't even have a statement. It's suppose that a function from A to B has non-empty domain, and that there is a g that goes from B to A, right? It goes the other way, which composes f to be the identity, right? So it does the same thing as f inverse, right? Then what do we know about f, right? And the answer should be that claim is the same as f being injective, which is the same as f being invertible. Okay, so fill in the if and only if f is injective, if and only if f is invertible. Okay, so let me draw a picture. Let's do it over here. Okay, so f takes us from the left to the right. G goes the other way. And G has the property that whenever I plug in f of x, it gives me x. So I need some colors. I don't know why I ever put these down. I always need colors. So if we plug in this guy here, right, who is f of x, we get g of f of x over here, right, and g has this bonus property that it spits out the original f. Okay, so a function that does this, right, a g, we call it a left inverse to f, because when you stick g on the left, it inverts it, right, it undoes the operation. Okay, so what this is saying, roughly, is if we have such a g, then it must be the inverse function, right? It must be f inverse over there, right? There's only one choice. Okay, and I proved one direction of this in class last time, so I won't reprove that. And the other direction is the trivial one, and that's why I got confused. So I think the trivial direction is if this g exists, then f is injective. And I think if it's injective, proving the g exists is a little harder. You have to build it. Proving it's injective is not too bad. So we could say, suppose f of x1, let me use capitals, equals f of x2, right? So this is one structure to proving things are injective, is you suppose you have two different inputs that go to the same output, and then you prove that you actually have the same input all along. So our goal is to prove that x1 equals x2. How do we do that? Well, suppose we have this g that goes from b to a, right? So I can plug both sides of this into g. Then right, I'm allowed to do that because the domain of G includes the range of f. Okay, but what do I know about G of f of a guy? Tell me. It just returns, yeah. So like this G of f, they undo one another, right? They cancel each other out. So I get x1 is x2, right? So provided you can undo f had to be injective, right? If two different things went to the same guy, then you can't undo uniquely. That's the summary. I'm probably overstressing something that you all understand. Okay. So, if you like thinking about these things, you can wonder about the case where A is the empty set and wonder why I'm insisting that A is not the empty set. It's not like an important thing, but you can work out where I implicitly use that A is not empty somewhere in the construction. Okay, so the reason I go through all of this in so much detail isn't because I think it's new, but it's because something very interesting happens when we ask about surjections. Okay? So being one-to-one is the same as having a left inverse. I think it's one-to-one. Oh no. All of my principles. Being injective is the same as having a left inverse, right? So you might think, and even know from math classes, that being surjective is the same as having a right inverse, right? Going the other way. So let's have a look at an example and see what I mean. And of course, the way I framed this makes it look like something's going to go wrong, right? Because I haven't put in a box the version. So something very, very subtle goes wrong. Okay, so what's a good surjection? ln from the positive reals to the reals. Okay, so let's have f from I wanted the domain and the range to be different, that's all. Just so we know what's what. All right, so the natural logarithm. Do you all believe me that that's surjective? Okay. Right, it's actually even a bijection. Which, yes?
Is the range just, or the domain, greater than 0?
Yes, it is, thank you. No ln of 0. Now it's surjective. Before it wasn't even a function. Okay, what's its inverse? Tell me. E to the x, right? E to the x. So, g goes from the reals to the positive reals. I mean, you can't, usually we consider it as a function from R to R, but if we do that, then our domains and ranges, our range isn't equal to our codomain, which is a little bit of a nuisance. Okay, so this example here, it works both ways, in the sense that g of f of x and f of g of x both make sense and are both the identity, right? So g of f of x, right, thinking in terms of left inverse, that's e of ln of x, right, which you know from your lives is equal to x. But also f of g of x, right, which is ln of e of x, also equals x. Okay, so this is thinking about g as a right inverse, right? It goes on the right. And this is thinking about g as a left inverse. It goes on the left. Okay, so this one, it works in both directions. And the reason is that f isn't just a surjection, it's a bijection, right? It's injective too, right? So the left inverse stuff comes from, like this stuff comes from extra properties of ln. Okay, so can we think of a function which is a surjection but not an injection? Tell me one. Tan? And yes, but its domain is complicated. So yes, I could use that one. I just want an easier one. Yes? X cubed minus x? Okay, that's from way back when, right? Get out of here. Okay, so this polynomial is x squared minus 1, right? Which is x plus 1, x minus 1. And now you can probably sketch it for me, if you couldn't before. Let's call this f as well, so I have a name for it. So it goes, right, so that's a surjection onto the reals, right, but not an injection because of this hill behavior here, right? So f goes from the reals to itself. That was a real question because all I could think of off the top of my head was the sine function, and I really didn't want to deal with arcsine because no one wants to deal with arcsine. Okay, so this function is not injective, right? Which means if I tell you your y value is, say, 1/2, you cannot tell me what x value I had, right? Because there's 3 different options, I think. I don't know where this peak is. I hope it's above 1/2. you can check. But the picture explains. However, we are surjective, right? So for each y value, there is an x value. Okay, so what would be a function going the other way? And it's hard to draw, actually, but you can do it. So I'm going to use all of this to here, this critical point, where I would start repeating. Then I cannot use this chunk, because I wouldn't have a function anymore, right, going the other way. And then you take that piece there. Right, which is, I'm sorry, the blue is not very visible, is it? I was trying my best. So the red. Okay, so if we restricted to, right, so those are supposed to be at the same height. If we restricted to that domain, suddenly this function is a bijection, right, and we can invert it. Okay, so what this means for us, right, is we can half invert, we can right invert, but we have to be careful about domains and ranges. So, like, inverting here, you have to think of the y-axis as your input axis, right? Because we're thinking about the inverse of the function that's drawn. When you plug in, say, 0 on the y-axis, you have to pick one of the points on the graph, and there's 3 options, right? There's 1 or 0 or -1. And the piece that the red piece that I've taken says choose 1. Does that make sense? Right? And if you're over here, you could choose this or this or this, right? For this particular y value, and I've said choose this. Okay, so I don't know a nice formula for this in terms of the cube root. Like, I just don't know one. But this is a function, right? It's like going the other way. So it says, if your y value is greater than whatever this is, right, the thing we're plugging in, then you're on this branch of the function. And if your y value is less than that, then you're on this branch of the function. And that's our inverse, right? All right, so so G goes from R to R as well, has some complicated formula. And we know that f of g of y is what quantity? So draw the picture. Pick a point on the y-axis, tell me where it lives on the graph, and then plug that point, that x coordinate, back into the original function. Where do you get? It's hard because you're having to think of y-axis as an input and an output at different points of a function. All right, so g of y says, find me the x coordinate of some point on the graph at height y, right? And it tells you which point to pick if there's options. All right, so you plug in your y value, you draw a horizontal line, you see where you intersect the graph. If there's options, go to the red piece. I mean, just always go to the red piece because I've drawn the red piece. All right, and then spit out the x coordinate of that point. Right, that's what G does. What happens if I plug that x coordinate back into F? Tell me. Do I get all of them? It's still a function, right? Indeed, yeah. I get the value of y I originally plugged in. It equals y. Right, the drawing here, right, is we start here. G takes us there, right? This is g of y. And then if I plug that back into f, I just go up and over again, right? That's what functions do. All right. So we don't really know a nice, tidy formula for g, but we do know what f of g of y is, right? It's the identity. On the other hand, g of f of x can get messed up. G of f of x is sometimes equal to x, but doesn't need to be. And the problem is, if you plug in a point which isn't on the red part of the graph, right? So if we start, say, here, this x-coordinate, f of this x-coordinate says go up to the graph and then go over to the y-axis. That would be f of x. And if I plug that into into g, what do I get? Do I get x again? The answer is no, right? Because I look along the line and I go to the red part of the graph. So I go over here and then down again. So this need not be equal to x. Maybe it is. Maybe it isn't. Okay, so we've just done a very complicated example about a surjection which is not an injection. And we've seen we can right invert, but we can't necessarily left invert. Okay, and the same is actually true with injections going the other way. You know what's a better surjection which is not an injection? X squared, because we do know the formula for the inverse. Okay, so onto its range. From the reals to the non-negative reals. I might make that a homework question, or you have to think about it yourself. Okay, so we did all this fussing, but it looks like we have injections that go along with left inverses, and we have surjections that go along with right inverses, and that should be they should be similar, okay? And they very nearly are, except that one of them, the surjection one, we can't prove on the axioms, based on the axioms we have so far. Okay? So if you remember back to the injection proof, which unfortunately happened last time, I had to tell you what to do on an input in B, which is not in the range of F, right? If you remember back to last class, right? There was, if you're in the range of F, just go back. If you're not in the range of F, I have to tell you what to do, right? Because I'm defining what G is. And I just said, pick a point. Okay, so there we had an option, right? We had choices, and we made one. We said, whenever F doesn't tell you what to do, go there. And that's where we use non-emptiness of the domain. Here, we had to make choices as well. So whenever we whenever we had a point where we're like not injective, where F is not injective, right? I have to tell G what to do. And it has multiple options, right? Like looking at the yellow line again. I want to tell G what to do when I plug in the height of the yellow line. And I have to say, pick one of these three. It doesn't matter which, right? But pick one of the intersections of the graph. So you might be like, okay, we'll just pick one. And that's going to be G of Y. Okay, then I say, okay, but you need to do it for all of them. Right, this whole vertical chunk here, you need to make choices for every single Y. Right, and I did here, right? I said choose the red piece whenever you can. Whenever there's a choice, choose the red piece. Over here, we made one choice, right? I didn't say for each thing not in the range, choose at random. I said go there, all of you. I make one choice once. Here, we have to make infinitely many choices, right? I have to tell you what to do on this whole range. And that wasn't hard for us. We could say, choose the rightmost piece, right? I gave you a rule. Choose the rightmost option. But the problem that occurs if you try to prove this is that if f and a and b are very abstract, then there's no particular reason to choose one value over another. So you end up making choices arbitrarily. And our set theory just does not allow us to make infinitely many arbitrary choices at once. It's not that we can't do it as human beings, it's that our axioms cannot do it for us. Okay? So now we get to talk about the axiom of choice. Is this making sense, or am I talking too abstract? I don't know, man. I think the thing that Russell suggested was, let's suppose you have infinitely many pairs of shoes, right? And we want a function that goes from pairs of shoes to one of the shoes in the pair, right? So it chooses a shoe, right? And our set theory can actually produce that function because we can say, choose the left shoe, right? So we're not actually making infinitely many arbitrary choices. We're making a non-arbitrary choice, right? Because we said, choose the left shoe. However, if you have infinitely many pairs of socks, I can't distinguish left sock from right sock, right? They don't look different. So if you're trying to make choices, you have to keep making arbitrary choices forever. And our set theory just doesn't let us do that. Yes?
Does saying pick the left shoe count as like one arbitrary choice or no arbitrary?
I mean, it depends on, arbitrary isn't like entirely well defined. Like it's arbitrary in the sense that I could have chosen right. What I really mean is there a rule which assigns you that lets you make the choice? So yes, you can make, we do make arbitrary choice of left over right, and you could say on this one choose the right one and then everybody else choose the left. Our set theory lets you do that. But if we're trying to, if at one point you just say choose somehow, and I'm not going to tell you how to do it, and you have to make that choice infinitely many times, that's the no-no. Okay, so axiom of choice, surjection split. Okay. So people get antsy about the axiom of choice, and the people who get antsy about it really don't understand it. Because if you reject the axiom of choice, you have to reject the existence of right inverses of surjective functions. They're equivalent statements. So the axiom of choice does imply some weird things, but if you want every surjective function to have an inverse, you must accept the axiom of choice. They're equivalent. Okay, so axiom of choice, V1, which I'd call all surjections split. How did I phrase that in my notes? Let me be consistent. Okay, so it says, if R is a relation, then there is a function H, which is a subset of R. We'll talk about that a little more shortly, with the same domain as R. So remember, a relation is a set of ordered pairs, right? So I can have subsets of it. It's a set. Okay, so what H is, right? It is a function. It has some of the pairs from R, not all of them necessarily, but it has some of them, but it has the same domain, right? So for everything that's the first coordinate of something in R is the first coordinate of something in H. Okay, so the way we can think about this is R is trying to be a function, right? It says, take an X value, here are all of the arrows going out from me towards Y's. And it's not a function because there can be more than one arrow. H picks one of the arrows and says, this is my guy. So a very simple example. here's a relation, right? 1 is related to A and to B. 2 is related to A and to C. There are many possible H's. So H has to have the same domain. So we have to tell H, the function, what do I do on 1 and what do I do on 2? And you have to follow one of the arrows because you're being a subset of H. So one choice, I put my colors down again like an idiot. There you go. That's one choice for H. Can you see the red? It's a little dark, right? I don't know, man. People at the front can. So it's the trade-off for being uncool by sitting at the front. You do get to see, which is helpful pedagogically. I've sat in the back of every class my entire life, just so you all know. And I dress like this, so that's a sign of where you're all at in the great hierarchy of cool. All right, so here's... okay, so you see what I mean by... this lets you choose the arrows. Let's imagine the sock example again. So there's like a relation between pairs of socks and socks, right? So to the pair of socks is related to each of the socks in the pair, right? So right now I'm wearing these guys, which are bamboo. They're very comfortable. Okay, so there's 2 of them, right? And that's an object for us, right? The set of those 2 socks is an object in our domain, and it's related to each of the socks in the pair. I also have some socks with some corgis on them, right? So the pair of that socks is over here, and each sock separately is over here, and the arrows go that way. Okay, so that's a relation, right? Pairs of socks to the sock in the pair. It's a very strange relation, but it is a relation. You can also think like bricks inside of a building, right? The building is an object, and it's related to all of the bricks that make it up. It's a relationship between buildings and bricks. Okay, so that's a relation because there's more than one brick or more than one sock. And H would say, give me a building, I'll tell you a brick. Or give me a pair of socks, I'll give you one of them. Yes?
Do we have to make a choice for each object in the domain, or does that matter?
Yes, it must have the same domain. If I didn't insist that the domain was set the same, I could choose H as the empty set, because that's a function and a subset. Yes?
How are we exactly defining subset? Like, can we define subset in the same way that we did it for sets? Because what do you mean is an element of each and an element of R?
So R is a relation, so it's just a set of ordered pairs.
Okay.
So in this example, R is the set 1A, 1B, 2A, 2C. Yeah. So here I am exploiting the fact that everything is a set. So if you draw it like with the arrows, a subset of the relation is pick some of the arrows. How are we all doing? What's time like? 9:48. That's an excellent break time, isn't it? Let's take a break, because then we get to play with the M&Ms.
It's not really good. The main range arrows. It's an excuse for them to go through. So I want to get some arrows. I just want to everything over here gets an arrow. It doesn't get one. It could be a function because it's not more than one. So
That's like
the domain to still have an arrow. Oh, yeah, that's true. That's straight up.
I don't need to.
Oh, okay.
Yeah. That's so chill. Oh, I
I love how it's showing like raising hell and
I take classes with the younger kids.
oh.
Sure. Okay, so the plan, the current goal is to find the first and quietly, because there are we need more than just to have electricity enough for the
Is it Cormac?
So what we want is
Fell off the going to class train like 2 weeks in.
find enough numbers to just
My counts drops too.
as expected. So I need these functions to allow me to do that challenge.
Then there's this where it's like, okay, let's getting half of it. It's 50 minutes to not go start. That's what analysis was like. And then the tests were pretty straightforward.
So this, well, this one here, you know, for me, I could describe this.
What? You gotta just straight up divide and conquer. Like we had a group chat of 16 people in analysis, and we're just like, all right, fast forward now.
Right, and that's what
Like
other
4 hours
functions
of excitement. I still want to.
if you have a function, that's pretty well behaved function.
And then work on my
If we function through alpha sitting number then there might not be a lot.
class after doing it.
Like, yeah, so then it becomes hard. Yes,
Yeah, still average. Oh, I still haven't watched that. You know what a geometric series is?
apparent.
Geometric distributions like 20 flips. Like times you flip it to get ahead. It's like the chance of getting ahead the first time is 50%. But you're still not getting ahead the second and fourth. And so it's just it's like exponential decay. But it was like at that point, and he just starts writing all these like Taylor series. I'm like, whoa.
That's like
Literally
literally
was sitting on that yeah, for the next 2 months. They would drop like at 2031. That's what I think. Like 17-12 on the 5K. I'm like, oh my. It's a fun game of like interrelation, right? Because you know like certain landmarks and you're just trying to guess. But they were dropping like the 6K tiles, that was 6K pictures. It's just automatic. And it's like 1 seconds per 10 minutes. So when you sit there like, oh shit, clear.
yes, that's what I mean. More than 4 butters.
It's like
passenger, there's 90% chance of showing. For your license, 10 tickets, for your license, 3 tickets.
yeah, there's the second follower. Yeah, that many it might dominate.
So you just want to choose one subset defined by overpowered by that problem. Okay, so the problem is that produces you all the functions.
The difference is like, you can't like, yeah.
Very literally no.
Yeah, it is.
And then arithmetic.
That'd be smart. Actually do injury prevention.
The difference is
You guys drag this like down the hallway.
Yeah, and we drag our road through the water. And we don't get knee injuries.
Without the extra choice.
Yo, the new one this morning was just simply
Yeah, right. So you're building the subset of it didn't prove that okay. You can build the set of square circles.
no, actually, well, I think you just got we got
It's not low, right? Yeah.
it's just the recruiting thing was for the recruiting. First case. If you witness stuff bad,
Okay, folks. Hi. All right. So the axiom of choice is now, well, you know one version of it. That's not, if you look up the axiom of choice, that won't be the version that's stated, but they're all equivalent given the rest of the axioms. I don't want you using choice in your homework because you don't need it. Okay? So if you ever say by the axiom of choice and you're in a homework problem, there was a way of making the choices explicit, and that's what I want you to do. Okay? So no choice for you. Yes, indeed. It's a good little joke about the Supreme Court. What a world. All right, so I guess I forgot that I had to introduce some notation. Abortion's a human right, by the way. Let me just make that clear. So I want to introduce some notation because I've been using it informally a bunch, and we can make it formal, and then you can use it. And people have been using it in their homework, and I don't want them to like lose points for using stuff that's we've only introduced informally. Okay, so we defined big union of A, right? That's the set of things in A, right? It's the elements of A. Okay, and I said what you want to do is think about this intuitively as list out all of the elements of A somehow, right? And already we're in trouble situation. What does it mean to list things? But we have an intuitive idea. And then big union of A is going to be A1 union A2 union A3, right? And so on, right? So I just want to make this concrete. Right, and I guess another way you could write this is this. So by analogy with like sigma notation, the union as I goes from 1 to infinity of A sub I, which like necessarily requires A to be countable, but there we are. Okay, so this is actually how people think about infinite unions all the time. This is quite, if you go into other classes, no one will know what you mean if you write down this. They only know what you mean when you write down this. They would also accept the union of A in A of little a, like that would be allowed in other classes, because they say, okay, take all of the little a's, throw them together, and they mean this. Okay, so we can like make this formal by something somewhat unpleasant called indexing. Okay, so what we did here is that we listed the elements of A, right? I gave them names. So I gave this one the name A sub 1, or like you could just name it 1, right? Because of the sub. This one is A sub 2, or just 2, right? It's labeled by 2. So indexing a set just means giving names to things. And we can abstract that as a function who takes in the name and spits out the thing it names. If you prefer, it takes in the signifier and spits out the signified. This is America, so semiotics is like big here. It is. Okay? So naming is a function that takes in a linguistic object and spits out an object, right? So like James is a sound, and it's also a word, but it is the act of naming is plugging that into the naming function and spitting out me. Okay, so that's what indexing is. All right, so using that abstraction, we can define all this stuff. Okay, so given a set I, which we think of as our indices or our names, right? So this is our set of names, and a function f whose domain includes I. This is a point where the book decides to be unnecessarily general. So the domain of F has all of the things in I in it, and maybe some other stuff that we're not worrying about. But you can just assume the domain of I is F. Sorry, the domain of F is I by taking a restriction. It's fine. So if you prefer, the domain of F is I, right? So F is the function that does naming. So you have names, namer, and then what's named is its range. Okay, then big union over the i's in big I. I'm sorry, it's really hard to draw i's on a lowercase I on a blackboard. That's an I. I can draw it like that if you prefer. Is that better? I don't know. So by this, what I mean is, my F of I is the object which is named by I via F. And I want to union them all together. I want to do this. Right? So for us, what do we have to do? Well, that's the big union of the set containing F of I for each I in our index set. So think about what this means, right? Big union, our official definition, means elements of elements. So the big union of this is all of the elements of things which are equal to F sub I. Right? So this literally equals like F sub I union F sub I prime. Right, this is intuitive. Intuitive equals. Okay, so I guess there's two ways to understand this. Number one, this means what you think it means. Number two, we have this way of jimmy-rigging it up using our terrible definitions. Okay, so this is now official notation, and it means what you think it means. And it's defined via this unfortunate abstraction. Okay, also we can do the intersection. For this intersection to be defined, I need the I is non-empty. Because otherwise I'm taking the intersection of the empty set, and we haven't defined that. That's all. Right, I need to have named something to take an intersection. Okay, so as on the board, you can use index intersections and index unions to take unions and intersections the way you mean to. And often, instead of writing F of I when we're doing indexing, we just do subscripts instead. Subscripting is another way of writing functions. Right? It's a function from the collection of subscripts to whatever you're naming. Right? It's another kind of function. So often we write F sub I for F of I when we're doing indices. Okay? So then over here, our domain of our F, right, our index set, is the natural numbers, or at least the positive integers. Let me be precise. Okay. So that allows you to do unions and intersections, and you can, if you find this abstraction confusing, that's fine, you don't have to worry about it. If you like everything to be defined in terms of the set theory, then now it is. Yes?
Did this require choice?
Good question. So what does it mean to require choice? This definition require choice? No. Does proving there is anything in it require choice? Maybe. In particular, we'll get to that. In fact, for these, like, no, I'm not making any choices. I'm saying throw them all together, right? I'm giving you an explicit rule. But shortly, we're about to do something that does require choice. Okay, so the other reason we do indexing is to allow us to take large Cartesian products. Okay, so remember that A cross B, that's the set of pairs whose first coordinate is in A and second coordinate is in B, right? So recall, that's not an A. Okay. So if I wanted to form A cross B cross C, one way to do it would be A cross B and then cross that with C, right? We did it in a homework. Okay, and then keep going, right? We could take any finite length Cartesian product. But there are times when I want to have an infinite length Cartesian product. So I want to take infinitely many sets and then just like think of those all as coordinates and use that. So an example where you might do this is if you want to think of a sequence of natural numbers as an object. So take the Fibonacci sequence, for instance, right? 0, 1, 1, 2, 3, 5, 8, 13, and I can't remember the rest. Right, that goes on forever. That's an element of an infinite Cartesian product of the natural numbers with itself over and over again. Right? So 0, 1, 1. This thing is in natural numbers cross natural numbers cross natural numbers cross. Right? Because each coordinate lives in the corresponding space. Yeah? So an infinite sequence seems, you can interpret it as a member of an infinite Cartesian product. Okay, so, and so on. We can do this more abstractly, or more generally, I should say. So, I and F as before. Okay, so given I and F as before. Okay, so we have I is our collection of indices. F is the thing that tells you what an index means. And what I want to do is I want to take the product of all of the outputs of this thing. So if I wanted to form this, I would need f of I equals the natural numbers. Always, right? Okay, then this is how we denote it. Big pi for product. Right, big sigma is sum, big pi is product. We're multiplying together over the things in the index set. Why am I changing to h's? That's bizarre. I guess I'll stick with my notation and clarify. So I'm choosing to denote f sub I with h sub I instead of f sub I for reasons that I don't recall from when I wrote this down, but it was a few weeks ago. So I'm trying to take this product. Okay, so how am I going to think of this? So this is the set of functions whose domain is I, and who live in the union, whose range, live in the union of all of the h sub i's with the following property. F of I has to be in h sub I. Okay, this is extremely abstract. Let us try and understand what it means. So you can think of each I as giving you a coordinate to fill in. right? Three-dimensional space has 3 coordinates. You have an x coordinate to fill in, a y coordinate to fill in, and a z coordinate to fill in. What are you allowed to fill in to the ith coordinate? Well, we're supposed to be multiplying together all of the h sub i's. So in the ith coordinate should be an element of h sub I. So that's this. So this is the list of all functions, which we're thinking of abstracting this kind of sequence idea here, where the entry in position I lives in the right set, h sub I. Does this make sense? Maybe a little bit? I don't even know. Got some head shakes. Let's do an example. So let I be 0, 1, 2, etc. So that's the natural numbers, but I'm being concrete. So I'm using these to name things. What are they naming? It names an interval in the reals. Okay? So 0 names the interval 0 to 1. 1 names the interval 1 to 2. And so on. Does that make sense? Okay, so now, an element of the product of the h sub i's is going to be an infinite list of reals. In the 0th coordinate needs to be a real that lies between 0 and 1. In the first coordinate needs to be a real that lies between 1 and 2. And so on and so on and so on. Okay, so for instance, a member of this product would be 1/2, 3/2, 5/2. Does this make sense? 1/2 lives in the interval 0 to 1. 3/2 lives in the interval 1 to 2. 5/2 lives in the interval 2 to 3, and so on. So that's how we would think about it intuitively, but this is given by a particular function, and that function is f of I is I plus 1/2, right? 0 plus 1/2 is 1/2. 1 plus 1/2 is 3/2. Does that make sense? A little bit? Okay, so this abstract product operation here is actually extremely difficult to understand in all instances except where I is the natural numbers. When I is the natural numbers, it just means infinite lists where the entries live in wherever, like whatever came above them in the list. And it gets much more complicated if I is anything else, because you can't really draw pictures like this anymore. But, I mean, silly. This is kind of silly. But if you take R many copies of R, so what I mean is, let the index set be the reals, and let f be the function that just always names the real numbers, I could form the product of I in the reals of the reals. And so I have, for each real number, I have a coordinate which is a copy of the reals, right? And this object is going to be extremely complicated, right? A member of it is going to be a function that takes in a real and spits out a real. Those are members of this product. Yes?
I was wondering where we use the brackets in that example.
Because this is abstracting the notion of a sequence,